In a previous course, we have been looking at DC circuits. That is where voltages and currents are, for the most part, constant, at least as far as the supply sources are concerned. We are now going to go into the realms of AC circuits, where voltages and currents are not constant, but are changing rapidly. In our system in North America, they're changing 60 times a second, at least as far as the generation side is concerned. In other words, the supply source. So this is chapter 1, alternating current. With alternating current, it's possible to build electrical generators, motors, and power distribution systems that are far more efficient than DC systems. And so we'll find AC, or alternating current, used predominantly across the world in high-powered applications. The two diagrams you see in front of you are illustrating the comparison between AC power and DC power. The one on the left, the direct current circuit, is showing a battery, which is ultimately used for a direct current source, and you can see that the electrons flow is steady and it's flowing in one direction only, and you have a polarity that is constant across the system. In other words, the battery polarity is positive and negative, and if you were to measure the polarity across the load, which is a light bulb, it would measure positive and negative, and it would be steady. The diagram on the right is alternating current, and it's diagrammed such that it has a generator. In this case, it's a hand-driven generator, and it is constructed in such a way that the current is alternating. Half the time it's flowing in one direction, half the time it's flowing in the other direction. And if that change is fast enough, like we have in North America, 60 times a second, you don't even notice it in the flicker of a light bulb because it is too quick for your eyes or even the light bulb to null out and produce zero output. In a previous course, when we studied Faraday's law, we looked at a bar magnet that was thrusting in and out of a coil, and that was producing voltage half the time in one direction, half the time in the other. As long as you kept that magnet moving, the voltage was oscillating back and forth. So this would be, in no uncertain terms, a generator of sorts, very inefficient one, and it would be a reciprocating type mechanical action that was producing an alternating current. And if you did that 60 times a second, certainly you'd be duplicating or replicating the type of AC voltage that you would see in North America. However, that's definitely not practical, and in fact generators are built a little bit different than that. We usually, instead of a reciprocating magnet, we have a rotating magnet, which will cut, in this case, two coils that are set up in such a way that it'll push and pull the current in the direction that you want it to go in. If the magnet is in this position as it rotates, there's no current flowing because there's no magnetic flux cutting the coils. But as we turn the magnet, you get a maximum cutting of the magnetic flux in the case that the magnet is horizontal. So you'll get a push and a pull of a current in one direction. And as it rotates, it will go back to zero again. And as it rotates further, you'll get a push and pull in the other direction. So as the magnet goes in through several rotations, you will get a changing voltage. And if it's rotating at 60 cycles a second, you'll indeed get something similar to what you get in North America. And in fact, this is a very crude diagram of a generator. Generators are designed in such a way that you get a nice sinusoidal output, and the control is is governed so that it only turns at 60 times a second, and it's all packaged in a nice package such as you might see here in the way of a portable generator. When you get to bigger generators, of course, for the whole systems, you take the next step of practicality and you start to you generate voltages and transmission in terms of three-phase systems, which we'll cover in other courses. But right now, we're only dealing with single-phase AC circuits. And by the way, the theories that you will learn in this course are very similar and in fact are just extrapolated into the three-phase system, and the solutions you'll find are pretty much the same, except that you have to take into consideration that you have three voltages and three currents rather than one, and you have to know how they're related. However, that's getting ahead of ourselves. We're only talking about single-phase systems here. There is an effect of electromagnetism known as mutual inductance, whereby two or more coils of wire that are placed so that the changing magnetic field created by one induces a voltage in the other. If we have two mutually inductive coils and we energize one coil with AC, we will create an AC voltage in the other coil. When used as such, this device is known as a transformer. The fundamental significance of a transformer is its ability to step voltages down or to step it up from the powered coil to the unpowered coil. The AC voltage induced in the unpowered secondary coil is equal to the AC voltage across the powered, the primary coil, multiplied by the ratio of the secondary coil's turns to the primary coil turns. The transformer's ability to step AC voltage up or down with ease gives AC an advantage unmatched by DC in the realms of power distribution. When transmitting electrical power along long distances, it's far more efficient to do so by stepping the voltage up and then stepping it down at the end. The advantage here is you can use smaller diameter wire with less resistive power losses in the transmission process. Transformer technology has made long-range electrical power distribution practical. Without the ability to efficiently step up voltage or step it down, it would be cost prohibitive to construct power systems for anything but close range, within a few miles at most. As useful as transformers are, they only work with alternating current, not direct current, because the phenomenon of mutual inductance relies on the changing magnetic fields, and direct current, DC, can only produce steady magnetic fields. Transformers simply will not work with direct current. When referring to AC power in terms of voltages and currents, we loosely refer to the term AC voltages. When you think about it, it seems a little bit like a misnomer to call voltage alternating current voltage, but basically we refer to anything in regard to producing or being produced by alternating current as AC. So it's going to be helpful to understand what these AC quantities look like. Generators of AC quantities, or AC power, ultimately AC voltage and AC current, are designed in a special way such that the voltages and currents flow and follow what is known as a sinusoidal waveform. And sinusoidal waveforms, when removed from the time domain, are converted to rotating vectors or phasors, which lend themselves to trigonometric functions that help in the analysis of AC circuits. The magnitude of AC quantities can be described in several ways depending on the nature of the observation. The most useful of these is RMS, or root mean square values, which we are about to discover in this chapter. An alternator, or a generator, is designed to produce AC voltage in a specific shape over time. The voltage switches polarity over time, but does so in a very particular manner. When graphed over time, we call it the time domain, the wave traced by this voltage of an alternating polarity from the alternator, and it takes on a distinct shape known as a sine wave, or we can describe the wave as sinusoidal. This name will become more meaningful later in the chapter when we're looking at waves in terms of vectors or phasors. In the voltage plot from an electromechanical alternator or generator, the change from one polarity to the other is a smooth one. The voltage level changes most rapidly at the crossover point and more slowly at the positive and negative peaks. Because this is a repetitive cycle, we describe the wave in terms of cycles, where one cycle is divided up into 360 parts or degrees. So here we have that waveform, and it's divided up into 360 parts or degrees. And we're saying that the waveform goes from 0 to a maximum, back to 0 to a negative maximum, and back to 0 again. And that maximum or minimum in this particular case is 1, and it's proportional. So this 1 could be 1 kV or could be 100 kV. Because it's proportional, we're not putting a value on it right now. We're saying the maximum value is 1. Or the peak value or negative peak value is 1. So if we start this wave off at 0, in its 0 degrees, it starts off at 0. And if we go to 90 degrees, we are at a positive peak, and the value is 1, and we're 1/4 of the way through the waveform. At 180 degrees, which is halfway through the wave cycle, it is back to 0 again and on its way to a negative value. At 270 degrees, we are at the negative peak or negative maximum value, and in this case it's -1. And when we get to 360 degrees, then the value is back to 0. If we were to follow the changing voltage produced by a coil in an alternator from any point on the wave graph to that point when the wave shape begins to repeat itself, we would have marked exactly one cycle of that wave. This is most easily shown by spanning the distances between identical peaks, but may be measured between any corresponding points on the graph. The degree marks on the horizontal axis of the graph represent the number of degrees of the cycle and also the angular position of a simple two-pole alternator shaft as it rotates. Since the horizontal axis of the graph can mark the passage of time as well as the shaft position in degrees, the dimension marked for one cycle is often measured in a unit of time, most often seconds or fractions of a second. When expressed as a measurement, this is often called a period. The period of a wave in degrees is always 360 degrees, but the amount of time one period occupies depends on the rate of voltage or current oscillations back and forth. A more popular measure for describing the alternating rate of an AC voltage or current wave than period is the rate of back and forth oscillations. This is called frequency. The modern unit for frequency is the Hertz, abbreviated Hz, which represents the number of wave cycles completed during 1 second of time. In North America, the standard power line frequency is 60 Hertz, meaning that the AC voltage oscillates at a rate of 60 complete back and forth cycles every second. In other places in the world where the power system frequency is 50 Hertz, the AC voltage only completes 50 cycles every second. A radio station transmitter broadcasting at a frequency of 100 megahertz generates an AC voltage oscillating at a rate of 100 million cycles every second. Prior to the canonization of the Hertz unit, frequency was simply expressed as cycles per second. Older meters and electronic equipment often bore or still bore frequency units in CPS or cycles per second instead of Hertz. A period and frequency are mathematically reciprocals of one another. That is to say, if a wave has a period of 10 seconds, the frequency will be 0.1 Hertz, or 1/10 of a cycle per second. Frequency in Hertz equals 1 over the period in seconds. We encounter a measurement problem if we try to express how large or how small an AC quantity is. With DC, where quantities of voltage and current are generally constant, we have little trouble expressing how much voltage or current we have in any part of the circuit. But how do you grant a single measurement of a magnitude to something that is constantly changing? One way is to express the intensity or the magnitude in terms of its amplitude of an AC quantity. In this measurement is often referred to as peak measurement of the AC waveform. Another way is to measure the total height between opposite peaks. This is known as peak to peak value of an AC waveform. Still another way of expressing the magnitude of a wave is to mathematically average the values of all the points of the waveform's graph to a single aggregate number. This amplitude measure is known simply as the average value of a waveform. If we average all the points on the waveform algebraically, that is to consider their sign either positive or negative, the average value for most waveforms is technically 0, because all the positive points cancel out all of the negative points over a full cycle. However, as a practical measure of waveform's aggregate value, average is usually defined as a mathematical mean of all the points' absolute values over a cycle. In other words, we calculate the practical average of the waveform by considering all the points on the wave as positive quantities, as if the waveform looked like this. The average value would then have some value other than 0 that would be related to the intensity of the wave. So far, we have looked at 3 ways of measuring an AC waveform, and as a matter of fact, every one of these can be converted to the other by a simple mathematical constant calculation. And You can talk about peak or crest or peak to peak or mean average values and convert one to the other by the multiplication of just one simple conversion number. The thing that you have to remember, of course, is what you're measuring with, and to relate that to the people or the persons who is receiving the information. They have to be totally aware of which one of these methods that you are using. Each one is good and will relate the information, but how useful one is something that's open for discussion, and we will look at that as well. As we communicate the values of voltage and current with others in the industry of electrical power, as well as the related quantities of power, energy, ratings of different elements, we have to ask ourselves, how useful are using any of these terms, and is there some way of measuring the values that is the most useful way? This question was asked and answered a long time ago, and the answer was the RMS values. And before just jumping into the definition of RMS, which, by the way, is also mathematically related proportionately to the term amplitude, peak, peak to peak, average, and mean average by a constant, let's go there in logical steps. We are going to start with these two simple circuits. One is a DC circuit on the left, the other is an AC circuit on the right. What designates them being AC and DC is their source voltage. One is a DC source and the other is an AC source. Other than that, the two circuits are identical. They both have the same light bulb, and the resistance of the light bulb is the same, and we're going to designate that as RL. If we close the switch on the DC circuit, current is going to flow through the light bulb, and the light bulb is going to light up to a certain amount of brightness depending on the amount of voltage that we apply to the circuit. And Ohm's law will just let a certain amount of current flow. Now, if we close the circuit, close the switch and complete the circuit on the AC side, let's assume we can adjust that circuit so that the light bulb lights with the same intensity as the DC circuit. So there's going to be a certain amount of AC current flowing in that circuit. We don't know what that is just yet, but if the light bulbs are the only source of dissipating the electrical load, which it is, then if they light the same amount of brightness and they're identical bulbs, then the power dissipated in both circuits is the same. In other words, the average power, DC power, consumed by light bulb is equal to the average power consumed by the AC light bulb. What we would like to know is, what is that AC current? Because if the two bulbs light to the same brightness, dissipating the same power, then the current IAC must be equivalent in some way to the current in the DC circuit. Now let's take another step forward and take a closer look at that AC current that's flowing in the circuit. And we're going to call that current I. And over a period of time, that current rises to a maximum, goes down through zero, goes to a negative maximum, goes back up through zero, and up to a positive maximum, and then repeats itself over and over again in a steady state condition. The actual current itself will rise to a value, a maximum value, we'll call it plus I max. And it will go to a negative maximum we will call negative I max. If an AC supply is connected to a component of a resistance R, the instantaneous power dissipated is given by the instantaneous current squared times the resistance in that circuit. That's the power equation. And if we were to plot I squared on the same graph, it would look like this. It certainly has to be at 0 whenever the current is at 0, because squaring 0, you still end up with 0. And as far as the maximums are concerned, the square has to be a maximum when the current is a maximum. In the case of the positive, that's a no-brainer. It's just the square of the I max plus I max, but the square of the minus I max is a positive number because you're multiplying a negative times a negative. So that will also be I max squared. So, and I'm just writing the instantaneous power equation again for future reference. I'm going to get rid of some of the superfluous stuff on our graph so we can look at just the I squared graph that we drew there. And the graph rises to a maximum which is equal to I max squared in both cases of whether I is positive or negative. Now, if we wanted to find the average of that curve, we could take the average of all of those values, and basically it is exactly I max squared all over 2. That's the average, because you have just as much above the average line as below the average line. So if you wanted to come up with a number that represented the average of I squared, the average of I squared is equal to I max squared all over 2, which we just discovered from our graph. So if we were trying to calculate, or we wanted to calculate the average power would then be the average current squared times the resistance, which would be P average is equal to I squared average times RL. But we've already discovered that I squared average is equal to I max squared over 2. So the average power is given by I max squared all over 2 times the resistance in the circuit. Going back to the equation for the current average, the squared, the I squared average is actually the mean average squared current. And the square root of both of the sides of that equation leaves us with the I average is equal to I max all over the square root of 2, which is the square root of the mean average squared, which is a mouthful, and that's usually shortened to the root mean square of the current, or the RMS current. So the RMS current is the average current, the mean average current, and it is exactly equal to 1 over the root of 2 times I max, which was the peak value that we were looking at earlier, and 1 over the square root of 2 is 0.70710678818, and it goes on for a long time. However, a quick average value or a quick value is 0.71 I max. So if you want to find the RMS value for the current, you just take the peak value or the maximum value of the sine wave and multiply it by 0.71, and you would have a pretty close approximation of what the IRMS is. And the RMS value for an AC supply is equal to the direct current, which would dissipate energy at the same rate in a given resistor or light bulb or circuit, if you would. We can use the same logic to find RMS value for voltage of an alternating voltage supply, which is the VRMS is equal to the maximum voltage divided by the root of 2, or multiplied by 0.71, where Vmax is the maximum or peak value of the voltage, and it's the same equation that we use for IRMS, I max all over root 2, where I max is the maximum or peak value of the current. So if we are looking at AC circuits for resistance loads only, and we'll get into different kinds of loads later, but this is for resistance loads only, the P average is equal to the current RMS value of the current squared times the resistor. And Ohm's law can be stated in terms of RMS values as well. VRMS is equal to IRMS times R. You can rewrite that equation in terms of R, where R is equal to VRMS all over IRMS. So the P average, if we substitute for R, would give us IRMS squared times VRMS all over IRMS, while the IRMS cancels out one of the squared values, and that leaves us just with the average value in a resistance circuit for the power is the RMS current times the RMS voltage. And remember, this is for resistive loads only. And that brings us to the end of Chapter 1.